Hi everyone, we're back with video number 4 in this module. We're still talking about what sugars are in grapes and reviewing carbohydrate chemistry. So we looked at the ring closing reaction and we said that that results in a hemiacetal of glucose. And the other thing that's really important is that anomers result from the ring closing reaction. And so what that means is when the hydroxyl group attacks the carbonyl, it can attack above the plane of the ring or below the plane of the ring. So this hydroxyl group here, it'll end up either above or below the plane of the ring. So this oxygen here was the one that was on carbon 5, and it's nicely color-coded in this picture. And this oxygen that I've circled here is the oxygen that was in the carbonyl. So that'll either be above or below the ring, depending on which side of the ring the hydroxyl oxygen from carbon 5 attacks. In this picture here, we show the hydroxyl group at carbon 1 on the same side of the ring as carbon 6. So there's carbon 6. That is the beta anomer. If it was opposite and the OH was below the ring, this OH was below the ring, and the carbon 6 was above the ring, they were on opposite sides of the ring, that would be the alpha anomer. So this one is beta D-glucose, or glucopyranose, pyran being the 6, indicating it's a 6-member ring. The beta D-glucose, glucopyranose, is called beta because the hydroxyl and carbon 6 are on the same side of the ring. So important distinction when it comes to ring closing and the chemistry of carbohydrates. And the reason is the linkages, whether they be alpha or beta, are subject to breakage by enzymes. So when we break down sucrose, for example, that's a disaccharide. Our enzyme sucrase breaks down the linkage in sucrose. All right, the enzyme sucrase breaks down the linkage in sucrose. And sucrase only breaks down the sucrose linkage. If the linkage was changed, then you would not be able to break it using that enzyme. So cellulose, for example, is a long chain of glucose molecules with a beta 1,4 linkage. And we'll talk about the 1 and the 4 in a minute. We don't have enzymes in our body to break down cellulose, and that's why plant material will just pass through us undigested. Here's another look at the ring closing reaction showing the alpha and beta products both. And so here is the straight chain we looked at before. It's bent around so the carbon 5 hydroxyl is close to the carbonyl. That hydroxyl attacks the carbonyl and you get either an alpha D-glucopyranose or a beta D-glucopyranose. So again, alpha results when this hydroxyl is on the opposite side of the ring from carbon 6. Beta results if the hydroxyl is on the same side of the ring as carbon 6. So these are anomers of one another. And we call this carbon right here the anomeric carbon because it's around that carbon that the conformation changes. Okay, so that's the anomeric carbon. And you can always pick that out because it's the one bound to 2 oxygens, as shown there. We looked at the formation of hemiacetals and said that when the ring closes in glucose, for example, you form a hemiacetal. Acetals are similar in that they start with a reaction of an alcohol and an aldehyde But acetals are actually the reaction of two alcohols with an aldehyde or a ketone. All right, two alcohols reacting with a carbonyl group, either in the form of aldehyde or ketone. So we looked at this picture here on this page. We looked at it right up to this point here. All right, and we reacted one alcohol, which I'm circling now, with one carbonyl. Now we're going to add a second alcohol. All right. So in this case, the way this mechanism is written, it starts again with protonating this group here. Remember, we started before by protonating the carbonyl oxygen to put that positive charge into the mix. Now we protonate. We end up with a positive charge here in panel 5 on this picture that I'm circling now. And then our second alcohol comes in and can attack that carbon right there. And again, there's going to be a partial positive charge on that carbon. And so the lone pair on the oxygen of the alcohol is going to attack there and form a bond. And so the result is going to be panel number 7. So here you have an acetal. An acetal is a carbon bound to two oxygens, each of which has an R group attached. All right? Remember, in hemiacetals, we had a carbon attached to two oxygens. One of those oxygens was in a hydroxyl group. In an acetal, both of the oxygens have R groups attached, right? And those R groups came from the two alcohols that we reacted with the carbonyl. All right? So, two alcohols, one carbonyl. The two R groups that end up on the acetal come from the two alcohols. All right? Why are we talking about this? We're talking about this because another important part of carbohydrate chemistry is the formation of linkages. And the linkages can be between two sugars, like we're looking at here, or between, for example, an aroma molecule in wine and a sugar. So remember, way back in video 1, we talked about the fact that, or was it video 2, that many aroma molecules are conjugated to sugars, and they're conjugated with a glycosidic linkage. So let's look at a basic glycosidic linkage first. In this case, we're looking at two glucose molecules. So you see the anomeric carbon that we just talked about. And in this case, attack is going to come from the hydroxyl group at position 4 of the second sugar. All right? So once it attacks, it forms a glycosidic linkage. And the glycosidic linkage creates an acetal. So you see there is the anomeric carbon, and now we've got two oxygens bound to it, each of which have an R group attached. The second R group is actually the second glucose molecule, and that is attached at position 4. So this is a 1-to-4 linkage, and because the oxygen here on the anomeric carbon is on the opposite side of the ring from carbon 6, this is an alpha 1,4 linkage. So it's a glycosidic linkage, alpha 1,4, and it links two glucose molecules, and those together create maltose. So maltose is a disaccharide with two glucose molecules. So alpha 1,4 glycosidic bond, that's the glycosidic linkage between the alpha anomeric form of carbon 1 on the first sugar and the hydroxyl that was on position 4 of the second sugar. All right, so we see those linkages all the time. I mentioned in the last slide that cellulose was a beta 1,4 linkage, and we don't have the enzymes to digest a beta 1,4 linkage. Luckily, we can digest maltose, and we have maltase in our bodies to digest an alpha 1,4 linkage. I had to remember for sure if we had that enzyme in us, but we do. Similar lactase. Remember, you'd think of lactose intolerance. People without lactase can't break down lactose. Lactose is another disaccharide. So normally we have lactase and we can break down the sugar in milk, lactose, but lactose intolerant folks don't have that functioning enzyme anymore, and they can't break down lactose, which leads to lactose intolerance. Okay, so let's look at O-glycosidic linkages. And I didn't mention this before, but the O in the O-glycosidic linkage means it's an oxygen that links the two, in the former example, the two sugars to form maltose. All right, so it's an oxygen. You can have N-glycosidic linkages when an amino group actually attacks a carbonyl, and we may or may not look at that in this class, but there are N-glycosidic linkages in nucleotides, for example, in DNA. So here we start with this alcohol and say it's going to attack a sugar. So we're all set up for attack, right? We have already protonated the carbonyl oxygen. So, and protonation promotes attack by a weak nucleophile. Again, alcohols are somewhat weak nucleophiles. So protonating that gives this carbon a larger partial positive charge, partial negative, of course, on the oxygen. And therefore, the nucleophilic lone pair on the alcohol hydroxyl group will attack that carbon. And so that's how it can start. And then you form this linkage. So there is your glycosidic linkage right there between those two carbons. The one carbon that originated in the alcohol, right? So this R group comes from the alcohol. And the other carbon, of course, was in the sugar. So you now have an O-glycosidic linkage. We haven't defined what this R group is that was in the alcohol, but it could be many different things. And it could be an aroma molecule in wine. You see that we also generate H2O when we form these glycosidic bonds. I didn't mention that earlier, but an OH and an OH from one molecule and a hydrogen from the other are liberated. So we liberate H2O. So this is a dehydration reaction because we get rid of oxygen from the two reacting molecules. So we form an O-glycosidic linkage there. In this case, the glycosidic linkage is on the opposite side of the ring as C6. So this little box is wrong. This should say opposite for alpha. And beta is going to be on the same side of the ring. So in this case, we have the oxygen on the anomeric carbon on the opposite side of the ring from carbon 6. And so that makes this an alpha glycosidic linkage. All right, that's it for topic 4. Thanks for watching. We'll pick up some more carbohydrate chemistry and apply it specifically to aromatic molecules in wine, or aroma molecules, I should say. And we'll see you then. Thanks for watching.